Well, thank you so much for coming out to hear me speak today about my ongoing journey to the Antarctic. Spoiler alert, I have not been to the Antarctic, but it is in the 5-year plan and I would love to go someday. So I will be talking about how I hope to get there and what are the steps I had to take to come and get here at this point in time. My name is Dasuma Khan. My preferred nickname is Ming. And today I will be talking about my own experiences, not representing any institutions, but really talking about my experiences throughout the world. So let's talk about Antarctica. It is the highest, coldest, windiest, driest of all places you can think about in the world. It is essentially a desert, despite all the water that we have there today. But it's a place that people are going to year-round. There are scientists that work in the Antarctic continent, about 4,000 of them in the summer, and about 1,000 of them over the winter. And as you can see from this map, there are bases all over the continent that are housed by different nationalities. But why do we go there? Antarctica is an important place because it is relevant to our understanding of habitat loss and climate change. This is very discussed in the world today, where beautiful seals and lovely creatures like that, the charismatic fauna, are losing out their spaces to be living in. But also Antarctica is just a wild and beautiful place, and that is why we want to go there, because as humans, we're inherently drawn to something that's beautiful and lonely, and it just boggles the imagination. But if you're getting more scientific, Antarctic science is the reason why we know about the harmful effects of chlorofluorocarbons. In fact, it was British Antarctic Survey scientists that discovered the massive holes over the ozone, in the ozone layer that were a result of common household products that contain CFCs, such as our refrigerators. And it is as a result of this that we have to wear sunscreen outside so we don't get things like skin cancer. So Antarctic science is important in many different ways. Antarctica is far away, right? But why do we care about it sitting here in the UK? Well, if we look at it not from the continental perspective that we're very used to, but rather from the oceans, this is how a fish sees the world. And when the fish is seeing the world, what they see is that Antarctica is at the very heart of it. Antarctic Southern Oceans are the only oceans that are connecting every other major water body on this planet. So global sea level, global weather, is all modulated and determined by the Antarctic circumpolar current, and therefore it is an extremely important location to understand. But more importantly, there's Bangladesh, which is where I'm from. There's the UK. They're not that far away from Antarctica because guess what? If there's ice melting at the poles, it enters into the Southern Ocean, which goes into the Indian Ocean, and then we get catastrophic sea level rise in a part of the world that we don't even relate to Antarctica ever. So Antarctica is very, very much at the heart of the entire world, despite us thinking of it as this lonely continent at the bottom of the ocean, at the bottom of the world. The Scientific Committee on Antarctic Research has 46 member countries, and these countries are all involved in Antarctic science in some way. Bangladesh's nearest neighbors, India and Pakistan, are members of the SCAR program. And so as you can see, it is really a truly global effort to be studying Antarctic sciences, but who's doing it in the United Kingdom? If we use the British Antarctic Survey, where I'm a PhD student, as a proxy for the people in the UK who are doing polar science, we can see that the demographics of UK society, where 16% of the population identifies people of color, Antarctic science is done by only 3% of the population. So there's clearly a lack of diversity within the field, and we're not entering that field for whatever reason. In this 3% study, I am actually not included because this study was concluded in 2021, and I started in 2021, so I'm not even there in that 3%. Tiny numbers of people. Very, very disproportionate to what the UK society actually is. So how did I get here? Well, here's my story. I'm a PhD student at the University of Cambridge at Newnham College, which is a women-only college, go girls, in the Department of Zoology and the Museum of Zoology and at the British Antarctic Survey. And I hold many different candles through these 3 institutes. But my background is very, very ordinary in that I've been all over the world, yes, and we're going to go through a story of 5 different countries because that's what my educational trajectory took me on. But I'm from a very regular, average family. This is my family. We have a large extended family. This is very similar to what a lot of you in the audience probably relate to. We go on family holidays across the country. We meet our extended family often. This is usual. This is normal. This is what we do. But I always wanted to work with the natural world because I thought volcanoes were cool. Volcanoes are cool. I mean, they're pretty amazing. They're disastrous as well, but they're pretty cool. But I wanted to study the natural world, but it ended up being a bit of a lonely path because not many people want to do it. But I really love this picture of my water cycle project from 6th grade because my little brother at that point was like a cat and he liked to sit everywhere that he would fit. So he decided to sit on my project. I wanted to give a shout out to two of my teachers from school because they were the ones who taught me geography because I couldn't study earth sciences in my school. But at the same time, at A-levels, my school was only able to offer it up until the 11th grade. So I had to teach myself geography just because I wanted to study the natural world and take the A-level exam. So that was already a lonely path to be taking when you have no guidance because people don't usually study it. But that meant that I had to become a role model very early on. In 2012, I was one of the winners of the National Earth Sciences Olympiad in Bangladesh. And this was right before I was about to go to university. And so as a result, I had become the poster child for next year's competition for the National Earth Sciences Olympiad. Because when you walk a lonely path, sometimes you just have to be the role model. So I got used to it fairly early on. And I think since then, many people from my school have decided that earth sciences are a great career path to pursue. And I'll tell you how right. I moved to the US, to Cornell University, to do my undergraduate degree in Earth and Atmospheric Sciences. But what I really wanted to show you are two different pictures, and the pointer's not working very well, so just bear with me here. My classmates and I are looking at a rock. We're looking at a road cut. It doesn't look very interesting from afar. But when you zoom in and look at that picture on the top, you can see fossils. Fossils of snails, of marine animals. This is upstate New York. I have a little map that shows you where New York is, upstate New York is. That is nowhere near the coast. And yet the rock record tells us that there are fossils in there that clearly belonged in the ocean. Why is that? Well, that's because 400 million years ago, the site that Cornell is in, upstate New York, used to be under a shallow sea. And it is the preserved remains of life of that time that we see today on the side of the road in the rock record. And I began to become very interested in the story that life could tell. But that's when I started running into a challenge, actually. I decided to go to New Zealand for 6 months to learn how to do geological field mapping. I was extremely excited to be learning how the natural world works and how you're mapping it and understanding the stories in rocks. I look quite happy in these pictures. I look very sure of myself in these pictures. But actually, this was one of the worst times of my life because this is when I kind of felt like perhaps being outdoors and in the field was perhaps not for me. And that's because I faced a lot of casual racism. And I had a very steep learning curve, which at the time that I did my field camp, which was in 2016, people had no idea how to respond. I had no idea that I could actually raise a valid complaint to my instructors and seek support. But this was 2016 and things are better now, in that the exact same organization that I did this with has since then undergone sensitivity training, interracial bias training, and things like that. And so things are better now. The field as a whole has realized earth sciences has a diversity problem, and a lot of it is because the field itself wasn't very welcoming. So things are better now, but in 2016 it was not so easy for me. But I just want to put it out there to say that as scientists, we might seem like we know what we want to do from the very beginning, but oftentimes we actually are not so sure of ourselves and have to find out ways to recover from that. So that's what I had to do. I came back to Cornell, returned to the US, which was very much my happy place. I absolutely love upstate New York. And I began to be interested in Antarctic fossils because that block over there are all marine fossils in Antarctica, and they look exactly like the snails we find in Bangladesh today. And I was interested in learning how they formed. Why is this rock essentially composed entirely of snails? I did my senior thesis on these Antarctic fossils at the Paleontological Research Institution, which is an affiliate institute with Cornell University. And when I graduated, my family made this giant big trip to the US because it's a special occasion. So I was very, very happy to be able to show off where I spent 4 years and where I had learned so much. And my family were so excited to be there. And I was also really excited about showing them off because they'd all heard stories. My professors heard stories, but nobody had ever met them. So this was a massive, wonderful opportunity. After I graduated, I decided to take a little bit of a segue. And that segue was I decided to work in geophysics. And so I worked at Cornell at what was at that time called the Cornell Energy Systems Institute to work on an enhanced geothermal system. And the reason for that enhanced geothermal system is that upstate New York is extremely cold. And if you want carbon neutrality, it's not electricity that's the problem, but rather heat. Heat is what you have to consider if you want to be carbon neutral. The whole idea of the Earth Source Heat Project was to drill into the Earth's surface, into the Earth's interior, heat up water through the natural heat in the reservoirs, bring that back up to campus, and heat campus in a more sustainable way than natural gas, which is what was currently being used. Massive, ambitious project. It is still working on. But when I was working on it in 2019, it was not glamorous. This is what we look like. We sat on trucks, we scrubbed seismometers, we put seismometers in the ground, and the reason why we were doing that is because it was such a novel idea, and we had absolutely no idea if it was going to work. So we needed to map what was underneath the Earth's surface through seismic methods, through gravity methods, and through fracture mapping across the entirety of New York State. So it was a whole lot of manual work that didn't look very glamorous at that time. But now, if you do a Google search for Earth Source Heat, you get massive articles talking about how Cornell is doing something very innovative. And the US Department of Energy gave it a $7.5 million grant to keep doing the research. I went back to Cornell last year in the summer to see how things were going. We now have a borehole and a massive observatory because turns out our mapping results showed that there is promise in this project that they were going to do, and so you could feasibly drill into the Earth's interior and heat up campus that way. So right now we have a test borehole and a whole new observatory called the Cornell University Borehole Observatory. That's my supervisor, who's now always showing up and talking to these incredible communities about the research that we have to do. So Terry Jordan, thank you. I know you're not going to see this, but I had to say it anyway. My point with this whole story is sometimes the work you do is tiny and minuscule, and you might not feel like it's playing a big part. But actually, in the grand scheme of things, working in earth sciences is kind of a way of saving the world. I want to go back into education after I finished my time at Cornell's Earth Source Heat Project. And I did move to a different country. And this time, I decided to move to Germany. And this is where I did my master's in paleobiology at the Friedrich Alexander University of Erlangen in Nuremberg. But like everybody else, I too had a pandemic. And so that basically meant that I couldn't actually spend as much time outside doing the field-based courses that this program had promised me. I had to adapt and actually ended up doing an entirely computational project where I had to learn a lot of coding skills and a lot of technical literacy to be able to do computational paleobiology. Great skill, and it set me up for my PhD. But more importantly, in Germany, in our master's program, we started realizing that there is a problem in the field itself, and so we started to undergo sensitivity training. We participated in an intensive reading group called Unlearning Racism in Geosciences. We studied the ethics and coloniality of fossil collections around the world. And so over here, I started to feel really reaffirmed in my decision to study the natural sciences, because as you remember, in New Zealand, I kind of felt like this was not for me because I didn't feel welcome. But I had this incredible group of friends and mentors who made me feel like, despite my steep learning curve, I still belong outside and that they will be there to support me. But the technical skills that I learned, because I had a computational master, set me up for my PhD. And now we're gonna go someplace else. Where do you all think this photograph is from? Or this painting, really? Audience participation. Anybody? Sorry? Sorry, I couldn't hear you. A jungle. Yeah, sure, a jungle. Where do you think this jungle is? It's in Antarctica. Yes, of course. It's a trick question. But like Bangladesh. It almost looks like the tropics. Did anybody find the dinosaur in this painting? If you did, raise your hand. Where's the dinosaur? It's there behind the tree, right here. Once you see it, you can't unsee it.
Oh yeah.
This is an imagination. Fantastic, isn't it? It's great. This is an imagination of a painting by Bob Nichols of what Antarctica looked like 65 million years ago. 65 million years ago, Antarctica was still at the poles, but the Earth was a greenhouse climate. There was no ice anywhere on Earth. And we know this from fossils elsewhere. But we're going to get to that story because I will now talk about my PhD in 4 images. When I say I study Antarctic science and I'm a student at the British Antarctic Survey, everyone says, oh, so you study penguins. And I have to say, no, they're great, but I don't. I actually study everything else that lives in Antarctica, which are the small invertebrates, the seafloor creatures that are called the benthic organisms. And the benthos are actually the most important part of the food web because in the Antarctic biomass, they contribute the largest portion. There are about 20,000 species that live in the Antarctic that are not penguins or seals, but we only probably know about 8,000 of them. In the bottom left, you see some fossils. Once again, they're essentially snails. They look like they come from Bangladesh. That is what Antarctic life looked like 65 million years ago. And today, they look like soft blobs on the right-hand side. I love my blobs, and we're going to talk about the blobs in a hot second. But that's a summary of my PhD in 4 images. How do we have that painting from before? Well, let's go to Seymour Island. Again, not me, not yet, but let's go on an imaginative journey to Seymour Island. There's Antarctica, the continent, at the bottom. The red circle points you to that larger picture over there. Another red circle shows you Seymour Island. And Seymour Island is an extremely important island on the Antarctic continent because it covers this huge part of Earth history. On the left-hand side of Seymour Island, the rocks are about 70 million years old. At the right-hand side, they're about 30 million years old. So it's this one tiny island that contains 30 million years of Earth's history that is preserved in the rock record, and we can see massive changes in the Earth's climate as we go across this island. So once again, not me, but other people. Here's a photo from one of my supervisors about how you can find fossils on Seymour Island, which is relatively ice-free. There's no plants, there's no trees, sorry, there are no plants. There are plants, but there are no trees. But the lack of tree cover and the lack of permanent ice cover means that you can recover fossils easily enough, once you go there actually. But I haven't been to Antarctica, so how do I get these? Well, museum collections. Museum collections such as the ones in the Natural History Museum right here, and for me, the Paleontological Research Institution back in Ithaca, New York, and also right here not right here, but slightly further north, in Cambridge at the British Antarctic Survey collections. Museum collections enable us to study incredible archives of a life that we would not be otherwise able to see, because not everybody can go to Antarctica. It's very hard. I haven't been there and I studied it, but I studied it from museum collections. And a lot of these fossils look very similar to Bangladesh's marine life forms, and that is something that truly interests me, is that how do you get such similar looking organisms in such a different environment? Well, that's because, the world's diversity of life is fantastic. But they are very, very similar looking, some of them. But some of them are completely different. What is that? That is so confusing. It's like a paperclip. And actually, that's kind of how it has been described. It has been described as a paperclip ammonite, so it's a heteromorph ammonite. All these fossils tell us about a different world today. And what it's showing us is that painting I showed you earlier of Seymour Island on land, here's what Seymour Island looked like 65 million years ago in the oceans. You had mosasaurs, you had sharks. You don't have these predatory animals in the Antarctic continent today. They are not there. But you have the paperclip ammonite, which is kind of swimming around. You can't really see it here. So I'll get you to the next picture. This is what the paperclip ammonite used to look like, and we know this from the fossil record, and it's essentially a an octopus and a squid kind of mixed in one. It is this hilarious creature that doesn't exist anymore because they've gone extinct. But that was the fantastic representation and diversity of life back in the Antarctic. In the past, the organisms had hard shells. Today, they do not. They're dominated by soft, non-moving organisms, and they are what is considered to be the majority of the Antarctic life form, sessile suspension feeders. I showed you this picture earlier. How do I get this picture? Let's go back in place. The orange arrow shows us Seymour Island. The red arrows will show you the pictures where I get them from. But the pictures are essentially taken with cameras off ships looking down onto the sea floor. And so that is how we're able to observe the sea floor without actually going down. This stuff is very, very deep. It's 2,000 meters deep. People don't go there. And this is what the life form looks like now. Now I call them my blobs because I love the blobs, because they're great. You've got sponges that look like donuts. You've got a purple octopus up there. You've got another purple octopus on the right. In the middle picture, you have something that is green and looks like plants. There are no plants down there. Each and every single one of these organisms are actually animals, even if they look like plants. It's a biodiversity of an ecosystem that we can't even imagine, but we're able to see it based on photographs. And global collaboration with scientists along the world lets me be an Antarctic scientist while sitting at my desk in Cambridge, because the photos were taken by the German research vessel, the RV Polarstern, and that is the camera off the back of the Polarstern. And so that is the camera that is taking the pictures of the seafloor, and then I analyze them. But how do I analyze them? Well, here's a few examples of the photos. They don't look like a whole lot. These are all to scale, by the way. So that 50 centimeter brittle star, it's a sea star that's about like that big. Pretty big, giant sea star. And there is an octopus there. I hope people can't see it. I had a hard time finding it at the beginning. But what I do is I identify everything that is in the pictures. So I have to give them a name and I have to understand their biology. And this is how I occupy the vast majority of my time. What am I doing with this? Well, I'm trying to understand how the ecosystem functions as a whole. So if we have comics of the different organisms on the seafloor, what I'm trying to understand is how these different organisms are facilitated or helped by the other ones, such as, are they living together? Is one organism using the body of another one to help them catch their prey? For example, the brittle star over there often latches onto corals to be able to anchor itself and then swings its other arms to be able to catch prey. Sponges like to sit on little pieces of rock, and then sometimes there will be more brittle stars that sit on top of them. And so what I'm really trying to understand is how these organisms at small biological scales actually interact with each other. Antarctica is a great place. Antarctica belongs to nobody, and it belongs to everybody at the same time. We have a shared ecological heritage because based on the Antarctic Treaty, nobody gets to own it. Nobody gets to do economic activity there. Nobody gets to exploit its resources. And therefore, as people of the world, we all have a part in Antarctica, and we all get to actually participate in its wonders and appreciate them for what they are. But I'm going to end on a very different note. And that note is, today, Antarctica is at the bottom of the world. But in the not so far away past, I mean, it was about 200 million years ago, so perhaps quite far in the past, Antarctica and South Asia actually used to be connected in a place called Gondwana. So just for context, we have Antarctica, the white circle. Up top, if I can get the laser pointer, which it's there. It's just up there. I'll actually try pointing it on that one, if it shows up. But there is South Asia, that is the Indian subcontinent, and there's Antarctica. And it used to be connected. How did we move away? Continental drift. And so the Indian subcontinent rapidly separates from Antarctica, goes up the Palearctic Ocean, and connects with the rest of the Asian continent. And this is why, on the top of the world, in the Himalayas, the highest mountains, you get marine fossils. Because at one point, it was all underwater in a sea, and that is what got pushed up to the top of the world. South Asia and Antarctica have a shared geological heritage as well, and that's why we care about it. I have to thank all the people that were mentioned in the slides. my supervisors at Bass, at Cambridge, at Erlangen, in Cornell, but also I really have to thank my family because they let me do something that they had no idea about and believed in me and let me carry on with a path that was completely unknown to them. And with that, I'm going to share a picture of me with fake penguins, and there's me looking off into the distance and hoping that one day I can get to real penguins in the Antarctic continent. Thank you so much.